Welcome all. Now we are going to discuss theorem 10.5. The statement is let x and y be normed spaces. Then the first statement is if Z is a closed subspace of capital X, then the quotient map Q from capital X to capital X by Z is continuous and open. Okay, and the second one is let f from x to y be a linear map such that the subspace Z of f is closed in capital X. Define f tilde from capital X by Z of f to y by f tilde of x plus Z of f equal to f of x for x element of x. Then f is an open map if and only if f tilde is an open map. Okay, so we will look at the proof. First we have to prove that if x and y are normed spaces and Z is a closed subspace of x, then the quotient map Q is continuous and open. Okay, the quotient map Q is from capital X to capital X by Z and is defined by Q of x is equal to x plus Z. Okay, so we have to prove that Q is continuous and open. For that, we are checking the norm of Q of x. We know in the quotient space the norm is quotient norm. So triple norm of Q of x, which is the quotient norm of Q of x, equal to triple norm of x plus Z, and by definition that is equal to infimum of all norm x plus Z were Z element of Z. Okay, and being the infimum, it is less than or equal to each and every element of the set. So it is less than or equal to norm x plus 0, where 0 is an element of Z, we know. And so this is less than or equal to norm x plus 0, that equal to norm x. This means that triple norm of Q of x is less than or equal to 1 into norm x for every x element of x. So then by theorem 6.2 we can say that Q is continuous because it's in the form norm of Q of x is less than or equal to some alpha into norm x for every x element of x. Here alpha is equal to 1. So from using that theorem we can say that Q is continuous. Okay, now we have to show that it is open. For that, choose epsilon positive and a non-zero element x plus Z element of x by Z. We are going to show that Q is open using the theorem 10.4. Okay, so we are choosing a non-zero element x plus Z from x by Z. Then triple norm of x plus Z is clearly less than 1 plus epsilon into triple norm of x plus Z, because 1 plus epsilon is clearly greater than 1. Okay, so we know that triple norm of x plus Z is the infimum of all norm x plus Z where Z element of Z, and 1 plus epsilon into triple norm of x plus Z is clearly not a lower bound for that set. So by the properties of infimum we can find an element Z0, element of capital Z, such that norm of x plus Z0 is less than 1 plus epsilon into triple norm of x plus Z. Okay, this is clearly from the properties of infimum, because 1 plus epsilon into triple norm of x plus Z is not a lower bound. So there exists an element from the set which is less than that element. Okay, now let gamma is equal to 1 plus epsilon, which is clearly greater than 0. Also Q of x plus Z0 is equal to x plus Z0 plus Z by the definition of Q, and this is equal to x plus Z because Z0 is an element of Z, so x plus Z0 plus Z is equal to x plus Z. Okay, and norm of x plus Z0 is less than gamma into triple norm of x plus Z by using equation 1. Okay, that is we have arrived at the conditions of theorem 10.4, that is there exists some gamma greater than 0 such that for every x plus Z element of x by Z there is some x plus Z0 element of capital X with Q of x plus Z0 equal to x plus Z, and norm of x plus Z0 is less than gamma into triple norm of x plus Z. So by theorem 10.4 we can say that Q is open. So we have proved that Q is continuous and open. So this is the proof of the first part of this theorem. Now we are going to prove the second one. For that, x and y be normed spaces and f from x to y be linear map and z of f is closed in capital X, and defining f tilde from x by z of f to y defined by f tilde of x plus z of f is equal to f of x for every x element of x. Okay, now we have to prove that f is an open map if and only if f tilde is an open map. Suppose first that f tilde is open. Okay, so to prove f is open, we have to prove that f maps open sets to open sets. For that, let capital E be an open subset of capital X, and given z of f is a closed subspace in X, therefore we know x by z of f is a normed space with the quotient norm. Okay, so let Q be the quotient map, that is Q from x to x by z of f defined by Q of x is equal to x plus z of f be the quotient map. Then by the above part of this theorem, we can say that Q is continuous and open, because we have proved that the quotient map Q is continuous and open. So here Q is open. Okay, so if capital E is the open subset of capital X and Q is open from capital X to x by z of f, then we can say that Q of E is open in x by z of f. Okay, but also we have assumed that f tilde is open. So Q of E is open in x by z of f means f tilde of Q of E is open in y. Okay, that is f tilde composition Q of E is open in y. But we know f tilde is defined by f tilde of x plus z of f is equal to f of x, and Q is defined by Q of x is equal to x plus z of f. Combining these two, we can see that f of x is equal to f tilde of x plus z of f, which is equal to f tilde of Q of x. Okay, because Q of x is equal to x plus z of f, and that is equal to f tilde composition Q of x. This means that f is equal to f tilde composition Q. Then we can see that f tilde is equal to f composite Q inverse. Okay, let it be equation number 2. Then using that, we can see that f tilde composition Q is f, and so f of E is open in y. Okay, this means that if E is an open set in X, then f of E is open set in y, implies f is an open map. So if f tilde is open, then f is open. Okay, for the converse, suppose f is an open map, we have to prove that f tilde is an open map. For that, choose an open subset E tilde of x by z of f. We have to show that f tilde of E tilde is open. Okay, since E tilde is an open subset of capital X by z of f, and we know Q from x to x by z of f is continuous, and so Q inverse of E tilde is open in capital X, because for a continuous function we know inverse image of open sets are open. So E tilde is an open subset of x by z of f, and hence Q inverse of E tilde is open in capital X. And we assumed that f is an open map, and so f of Q inverse of E tilde is open in capital Y. That is f composite Q inverse of E tilde is open in capital Y. And also from equation 2, we can see that f composite Q inverse is equal to f tilde. So f tilde of E tilde is open in capital Y. This means that if E tilde is an open subset of x by z of f, then f tilde of E tilde is open in y, which means f tilde is an open map. So we have proved that if f is an open map, then f tilde is an open map. Okay, this is the proof of this theorem. Thank you.